Let's start our new session. Hello guys. आज हामी कङ्क्रिट टेक्नोलोजी अब्जेक्टिभको हेर्दैछौँ। लोकसेवामा कङ्क्रिट टेक्नोलोजीमा कन्स्टिट्युएन्ट्स एन्ड प्रोपर्टिज अफ कङ्क्रिट त्यहाँ 4 नम्बरमा दिएको छ। कन्स्टिट्युएन्ट्स एन्ड प्रोपर्टिज अफ कङ्क्रिट, फिजिकल केमिकल प्रोपर्टिज, water cement ratio, grade and strength of concrete, concrete mix design, testing of concrete, high strength concrete, pre-stressed concrete, admixture, यी छ। Constituents of concrete, cement, sand, aggregate and water. Constituents भयो कङ्क्रिटको। सिमेन्ट एन्ड स्यान्ड वाटर मात्रै भयो भने चाहिँ यो मोर्टार भयो। सिमेन्ट स्यान्ड एन्ड कोर्स एग्रिगेट पनि भयो भने यो कङ्क्रिट भयो। ल यहाँ अब हामी कङ्क्रिट टेक्नोलोजीको यो हेर्दैछौँ। कङ्क्रिट एज अ स्ट्रक्चर मटेरियल, वाट इज कङ्क्रिट? गुड कङ्क्रिट कम्पोजिट materials role. Cement is also one constituent of concrete, that is cement, sand, aggregate and water. Cement basic chemistry, taste on cement, types of Portland cement, types of pozzolana cement. पोर्टल्यान्ड सिमेन्टमा चाहिँ धेरै टाइप्सहरू छ, जसमध्ये अर्डिनरी पोर्टल्यान्ड, टाइप 1 सिमेन्ट, ऱ्यापिड हार्डनिङ पोर्टल्यान्ड सिमेन्ट अथवा टाइप 3 सिमेन्ट, स्पेसल ऱ्यापिड हार्डनिङ पोर्टल्यान्ड सिमेन्ट, लो हिट पोर्टल्यान्ड सिमेन्ट, मोडिफाइड टाइप 2 सिमेन्ट, सल्फेट रेसिस्टिङ पोर्टल्यान्ड ब्लास्ट फर्नेस, सुपर सल्फेटेड, व्हाइट एन्ड कलर्ड पोर्टल्यान्ड, पोर्टल्यान्ड पोजोलाना र अर्को एक्सपान्सिभ अर एक्सपान्डिङ टाइप पोर्टल्यान्ड सिमेन्ट, यो अदर पोर्टल्यान्ड सिमेन्टमा पर्यो। र पोजोलाना सिमेन्टमा हाई एलुमिनस सिमेन्ट र सिमेन्सियस मटेरियल परेछ। अब हामी चाहिँ ओके concrete is a structure material. What is concrete? Concrete is a material. Concrete is a material. What is concrete? Yes. Concrete is composition of cement and aggregate and water at certain proportions, and the strength and durability workability of concrete depends on the ratio of cement, sand, aggregate and also with the water cement ratio, that is proportion of concrete. We have referred to concrete as two-phase material, and we should now consider this topic further with special reference to the modulus of elasticity of the composite product. In general terms, a composite material consisting of two phases can have two fundamentally different forms. The first of this ideal hard material and which has continuous matrix of an elastic phase with the high modulus of elasticity and embedded particles of lower modulus. The second type is an soft material, which consists of elastic material with high modulus of elasticity, continuous matrix phase with lower modulus embedded with particles lower modulus. First type is hard phase of concrete. Transition phase. between hard material and soft material also occurs. Solid form, soft form, and the difference between the two cases can be large when it comes to the calculation of modulus of elasticity of the composite. In the case of composite hard material, in the case of hard material, composite hard material, it is assumed that the strain is constant over any cross section. Strain is constant while the stress in the phases are proportional to their respective modulus strength. Strain is constant over any cross section while stress is proportional to the material modulus of elasticity of the phases. Stress depends on modulus of elasticity. Strain remains constant throughout the cross section for the hard type material. In the case of our soft material, modulus of elasticity is calculated from the assumption that the stress is constant. Modulus of elasticity is calculated by the assumption that the stress is constant over the cross section, but the strain is proportional, inversely proportional to their modulus of elasticity. So, for a composite hard material, this is the lesson. For composite hard material, E equals to 1 minus G Em plus Ge P, where E is modulus of elasticity of composite material, modulus of elasticity is modulus of elasticity of matrix phase, Em matrix phase, Ep is modulus of elasticity of particle phase, and G is fractional volume of the particles. So E equals to 1 minus G Em plus Ge P, P particle phase, M matrix phase. 1 minus G is fractional volume. And the conclusion is the modulus of elasticity of aggregate is higher or lower than that of paste. Modulus of elasticity of aggregate is higher or lower than that of the paste, not equal to that of paste. The fact is that equation represents boundary for the modulus of elasticity of the composite. These equations here is the role of interface, that is hard, hard and soft form. Good transition from interface form. Interface phase. The properties of concrete are influenced not only by the properties of the constituent phases, that is two phase, that is hard and soft phase, but also by the existence of their interface, that is transition phase. So concrete मा constituent phase भनेको दुईटा हो, हार्ड र सफ्ट, र एउटा ट्रान्जिसन फेज भन्ने पनि भयो, बिचको interface, role of interface between the two constituent phases. One corollary of this observation is that the mechanical properties of concrete, such as rigidity, cannot be attributed to the mechanical properties of the aggregation of aggregate, but rather to the properties of individual aggregate particles on that of material. That the interface influences the modulus of elasticity of the concrete. The significance of interface is elaborated in chapter 6. Now, aggregate alone exhibit a linear stress strain. Aggregate alone exhibit linear stress strain relationship, and mm, so does hydrated knit cement paste, but the composite material consisting of two, that is concrete, but composite material consisting of two, that is concrete, has curve relation of stress strain. Aggregate has stress strain linear relationship, and but the concrete has curve relationship. The relationship of stress strain is not really linear due to the composite phases. The expressions interface is the explanation lies in the presence of the interfaces and known as the transition zone. This is transition zone, and the development of microcracks occurs at this interface under load. Microcracks are developed at the transition phases, that is, at the yes. Now the explanation is now the presence of interface is also known as transition zone. The development of microcracks at this interface under load. Microcracking occurs at the transition zone, that is interface phase of the hard and soft phase of the concrete. So these microcracks develop progressively at interfaces, making varying angle with the applied stress, and therefore there is a progressive increase in local stress intensity and in the magnitude of strain. Stress and strain. Thus, strain increases at faster rate than the applied stress, and so the stress-strain curve continues to bend over with an apparently pseudoplastic behavior. Stress is increasing. That strain increases faster rate than that of applied stress. So the relation between stress strain becomes pseudoplastic behavior, and curve the graph is curve in nature. Now uh, we are heading towards the mm, chapter 2. Chapter 1 मा mainly भनेको cement, sand, aggregate and water are the constituents of concrete, and concrete has two phases, that is constituent no composite phases that are hard and soft. This is uh, hard and soft phases, and that exist interface phase, also known as the transition phase between the two phases. And at transition phase, the development of microcracks occurs under the loading applied, and due to this transition phase is also known as the phase that determines the strength of concrete. Concrete strength is given by the transition state phase. So, and the strain stress relationship is non-linear, that is curve in nature for the concrete, but for aggregate, the strain stress relationship is linear. For concrete, the strain increases rapidly than the applied stress, so the relation becomes a curve in nature. For hard material, hard phase strain is constant, and but for soft phase stress is constant. And for the composite hard material, this is hard. Composite hard, not hard and soft. Composite hard, E equals to 1 minus G, Em plus EP. G is fractional volume of the particles. Em is modulus elasticity of the matrix phase, and EP is modulus elasticity of the particle phase. Now, the interface has the main role for the strength in this way. Now, our first constituent of cement. No, first constituent of concrete is cement. So, ancient Romans were probably the first to use concrete. Ancient Romans were the first to use the word concrete, Latin origin based on hydraulic cement, that is, material which hardens under water. Hydraulic cement means the material, that is, the cement that hardens under the water. This property and the related property of not undergoing chemical change by water in later life are most important and have contributed to the widespread use of concrete as a building material. The property of hardening at water and not undergoing chemical changes by water in later life are most important for the contribution of the use of this concrete as a building material. So, uh, Roman cement fell into disuse, and it was only in 1824 that the modern cement known as Portland cement was patented by Joseph Aspdin, a Leeds builder. Joseph Aspdin, firstly at 1824, this Portland cement was used, determined. Portland cement is the name given to a cement obtained by mixing together calcium and argillaceous or other silica, alumina, and iron oxide bearing bearing materials, burning them at a clinkering temperature and grinding in the resulting clinker. Manufacturing process. Now, basic chemistry of the cement. We have seen that the raw materials used in the manufacture of Portland cement consist mainly lime, silica, alumina, iron oxide. Mainly cement consists limestone, lime, silica, alumina, and iron oxide. This interacts with one another and complex products are formed. Series of complex product apart from a small residue of uncombined lime which has not had sufficient time to react and a state of chemical equilibrium is reached. Chemical equilibrium reached during the reaction of that is cement consists of limestone, silica, alumina, and iron oxide. Another complication arises from the interaction of liquid part of the with clinker with the crystalline compound already present. Four compounds are regarded as the major constituents of cement. They are listed in table number 2.1, that is, together with their abbreviated symbols. This shortened notation used by cement chemists describes each oxide by one letter, that is, calcium oxide by C, silicon oxide by S, aluminum oxide by A, and ferrous oxide by F. Likewise, SU is hydrated cement is denoted by H, that is main compounds in Portland cement. अघि भनेको थियो सिमेन्टमा के हुन्छ, क्ले हुन्छ, एलुमिना एलुमिना भने क्ले, लाइम हुन्छ, सिलिका हुन्छ, क्ले एलुमिना हुन्छ र आइरन अक्साइड हुन्छ। सो त्यसमध्ये अब एकदम डिपमा जाने हो भने मेन कम्पाउन्ड्स इन पोर्टल्यान्ड सिमेन्टहरू भनेको चारवटा छ अरे, ट्राई क्याल्सियम सिलिकेट, डाइक्याल्सियम सिलिकेट, ट्राइक्याल्सियम एलुमिनेट एन्ड टेट्रा क्याल्सियम एलुमिनोफेराइड। ट्राइक्याल्सियम सिलिकेट, डाइक्याल्सियम सिलिकेट, ट्राइक्याल्सियम एलुमिनेट एन्ड टेट्रा क्याल्सियम एलुमिनोफेराइड र सिमेन्ट केमिस्टले युज गरेको नोटेसनहरू सिमेन्ट केमिस्टले युज गरेको नोटेसनहरू क्याल्सियम अक्साइडलाई सी, सिलिकन अक्साइड एस, ए भनेको एलुमिनियम अक्साइड, एफ भनेको फेरस अक्साइड र एच भनेको हाइड्रेटेड सिमेन्ट। यहाँ भएको सी भनेको क्याल्सियम अक्साइड, एस भनेको सिलिकन अक्साइड, ए भनेको एलुमिनियम अक्साइड, एलुमिना एलोय, L2O3, एलुमिना एलुमिना क्ले, यो सिलिका SiO2 सिलिका यस, क्याल्सियम अक्साइड लाइम क्याल्सियम अक्साइड लाइम सी, सिलिका S, एलुमिना A, iron oxide F, and hydration H, hydrated. Four constituents are this: silica, alumina, lime, and iron oxide. So C3S, C2S, C3A, C4AF are the main four constituents of Portland cement. C equals to CaO, that is अलरेडी भनिसकेँ मैले, सी भनेको के हो, एस भनेको के हो, यो भनेको के हो, र फोर कन्स्टिट्युन्टहरू यही हो। अघि भनेकै सिलिका लाइम, सिलिका, एलुमिना, आइरन अक्साइड भनेकै यिनैहरू पनि यहाँ छन्। त्यही चारवटा कन्स्टिट्युन्ट मेन कन्स्टिट्युन्ट अफ पोर्टल्यान्ड सिमेन्ट, मेन कम्पाउन्ड्स इन पोर्टल्यान्ड सिमेन्ट तिनै छन् चारवटै। यहाँ अघि भनेको छ द पोर्टल्यान्ड सिमेन्टको मेनली लाइम, सिलिका, एलुमिना, आइरन अक्साइड, यो चारवटा कम्पाउन्डहरू मेन कम्पाउन्डहरू अफ पोर्टल्यान्ड सिमेन्ट भनेको छ। तिनै चारवटा कम्पाउन्डहरू यहाँ छ गरेको छ। र जहिले पनि चारवटा कम्पाउन्ड क्याल्सियम अक्साइड, सिलिका, एलुमिना, आइरन अक्साइड र एस भनेको SO3 सल्फर ट्राइअक्साइड, यो भनेको बक्स इक्वेसन फर द पर्सेन्टेज अफ मेन कम्पाउन्ड्स इन सिमेन्ट आर। मेन कम्पाउन्डहरू के छ, C3S, नो, मेन कम्पाउन्ड भनेको C, SiO2, Al2O3, A, Fe2O3, F हो मेन कम्पाउन्ड। त्यसमा C3S भन्ने बित्तिकै 4.07 C -7.60 S -6.72 A 143 F -2.85 SO3 C2S भनेको 2.87 SiO2 -0.75 हो। C3A C4AF भनेको यहाँ चाहिँ मेन कम्पाउन्डहरू छन् सिमेन्टको मेन कम्पाउन्ड एब्रिभिएटेड मेन कम्पाउन्ड्सहरू। सो मेन कम्पाउन्डहरूलाई पनि कन्सिडर गरेर चारवटा मेन कम्पाउन्ड्स अफ पोर्टल्यान्ड सिमेन्ट भनेको ट्राइक्याल्सियम सिलिकेट C3S, डाइक्याल्सियम सिलिकेट C2S, ट्राइक्याल्सियम एल्युमिनेट C3A, टेट्राक्याल्सियम एल्युमिनियम फेराइड C4AF यो छ। र यसमा चाहिँ क्याल्सियम अक्साइड कति, सिलियम अक्साइड यति यति र एउटा इक्वेसन यसरी फर्ममा लेखेको छ। यो भनेको बक्स इक्वेसन भन्छ यसलाई। हामीले पर्सेन्टेज अफ constituent main compound, percentage of main compound, that is percentage of main compound हामी डिटरमाइन गर्न सक्छौँ। यो BOUGES box equation for the percentage of main compound in cement को डिटर्मिनेसन गर्न यसरी गर्ने हो। C3S पर्सेन्टेज, CaO को पर्सेन्टेज, SiO2, Al2O3, Fe2O3, SO3 को पर्सेन्टेज हो भने हामी C3S को मेन कम्पाउन्ड C3S को पर्सेन्टेज निकाल्छौँ। त्यसरी नै C2S को नि पर्सेन्टेज निकाल्न सक्छौँ, C3A को नि गर्छौँ, C4AF को नि गर्न सक्छौँ। यसरी मेन कम्पाउन्ड्स अफ पोर्टल्यान्ड सिमेन्ट C3S, C2S, C3A, C4AF यो भनेको ट्राइक्याल्सियम सिलिकेट, डाइक्याल्सियम सिलिकेट, ट्राइक्याल्सियम एल्युमिनेट एन्ड टेट्राक्याल्सियम एल्युमिनियम फेराइड यो कम्पाउन्ड्सहरू हामी डिटरमाइन गर्न सक्छौँ यिनीहरूको पर्सेन्टेज यो बक्स इक्वेसन युज गरेर। यस्तै छ यहाँ। हाइड्रेसन अफ सिमेन्ट। The two calcium silicates C3S and C2S, that these are tricalcium and dicalcium silicates, are the main cementitious compounds in the cement. Cementing material भनेको these silicates हरू हो, and the former hydrating much more rapidly than the latter. यो C3S चाहिँ hydration rapidly हुन्छ than the C2S. In commercial cement, the calcium silicates contain small impurities from some of the oxide present in the clinker. These impurities have a strong effect on the properties of hydrated silicates. The impure C3S is known as halide and the impure C2S is belite. C3S impure फर्मलाई halide भन्छ, impure form of C2S लाई belite भन्छ। C3S र C2S चाहिँ सिमेन्टको स्ट्रेन्थ प्रोभाइड गर्ने मेन कन्स्टिट्युएन्ट हो। मेन कम्पाउन्ड चारवटा मध्ये मेन C3S, C2S, C3A, C4AF मध्ये C3S र C2S चाहिँ सिमेन्टिङ मेटेरियल स्ट्रेन्थ प्रोभाइड गर्ने, जसमा C3S चाहिँ ऱ्यापिड हाइड्रेसन हुन्छ, वाटरसँग ऱ्यापिडली रियाक्सन गर्छ भने C2S ले अलि ढिलो गर्छ। र C3S र C2S चाहिँ अक्साइड फर्मसँग सर्टेनली मिक्स भएका हुन्छन् र इम्प्योर फर्ममा एक्जिस्ट गर्छन्। सर्टेन इम्प्युरिटिज अकर हुन्छ त्यो C3S को इम्प्योर फर्मलाई हेलाइट भन्छ भने इम्प्योर फर्म C2S लाई बेलाइट भन्छ। हेलाइट इज द इम्प्योर फर्म अफ C3S, बेलाइट इज द इम्प्योर फर्म अफ C2S, and the product of hydration of C3S is the microcrystalline hydrate C3S hydrate भएर C3S2S3 बन्छ, माइक्रोक्रिस्टलाइन हाइड्रेट बन्छ with some lines separating out as crystalline. And C2S similarly, C2S behaves but clearly contains less lime. Now the calcium silicate hydrates are described as CSH form. CHS are hydrates of